Kia ora and welcome to NZGBC Plugged In. Today we have the second of our 3 lunchtime webinars for World Green Building Week, brought to you by the New Zealand Green Building Council. Thank you for joining today's webinar. I'm Amy from the NZGBC, and joining me today is Adrian Kerr, R&D and Compliance Manager at Temperzone Limited. Adrian has a background in science, energy and environmental management. He worked closely with ECA supporting the solar and heat pump water heating program during the late 2000s, before joining the R&D department at Temperzone. Welcome, Adrian.
Thank you.
But before we start, just a couple of house rules. You're muted during the presentation, but you can still send us questions through at any time. We will have a good 15-minute Q&A session after the presentation. Now's a good time to get out your phones and give us a tweet using the hashtag #BuildingLife. Most of you would have arrived by now, so let's do a quick poll before we start. Are you attending another World Green Building Week event this week? Great, it looks like lots of you are coming to another event. We're looking forward to seeing you there. I also want to thank our Plugged In webinar sponsors, Jib and Resine, and our World Green Building Week national sponsors, Bailey's and Temperzone, for supporting us. We couldn't do this without you. And now I'll hand over to Adrian. He'll be discussing the pathway to low carbon futures with HVAC in buildings. Over to you, Adrian.
Thanks, Amy and Isabel. Thank you for the opportunity to present today. Working to reduce greenhouse gas emissions has been at the centre of my work for the past decade, and it's a privilege to be here today supporting the work of the New Zealand Green Building Council during the World Green Building Week. Today, I'm going to talk about energy use in buildings, particularly in the area of heating, ventilation, air conditioning, and water heating. At its heart, this is an industry based on providing an indoor environment in which we can live, work, and play with a degree of separation from the outdoor environment. Unfortunately, the process of controlling our indoor environments is affecting our outdoor environment, which is the one on which we most ultimately depend. At Temperzone, we don't claim to have all the answers, but we have embarked upon a pathway dedicated to reducing the environmental impact of the products we produce. The air conditioning industry is a service industry, essentially providing purchase cooling capacity. The forms the cooling comes and differs greatly from platform to platform and from manufacturer to manufacturer, but they each contain the same core components of compressors, refrigerant, fans, and heat exchangers. Heating systems, on the other hand, are quite different. Where cooling is also required, space heating is readily achieved with a reversing valve. For dedicated heating systems, the choices are diverse, as are the associated capital costs. Gas is ever increasing in its market share, and if we are to lower carbon emissions, this needs to be reversed. For it is heating systems that are the key contributor to operational carbon emissions from buildings, and is the area for where there is the greatest potential for change. In most buildings today, heating is a service, and we need to transform the industry from a service mindset to focus on efficiency. Refrigeration has a key role to play. Heat pumps offer the greatest potential for the efficient use of a largely renewable electricity sector. Other options where practical are the increased use of biomass and solar. In this talk today, I'm going to look at the key drivers for change within our industry areas to focus on addressing, and to end with some illustrative projects we've recently undertaken. But before we get in too deep, there are a few generic points I'd like to make. And firstly, ours is a highly regulated industry. Most of our products are covered by minimum energy performance standards. However, MEPS applies at a product level. Work to make products efficient are very often undone at the system installed level. Poor implementation of controls, high-static fans pushing into undersized ducts, poor servicing, poor unit selection and configuration. The list is endless. As our products are becoming more complex to improve efficiency, the skills needed to service and support them is also increasing, yet the availability of these skills seem to be declining. Ours is also a highly demarcated industry between the trades and the different engineering disciplines. Often the outcome is better where there is integration between different parts of the building energy system, yet there's projects face regulatory and cross-discipline barriers which are very hard to overcome. And finally, the regulatory environment is slow to change. For example, the recent update to the MEPS standard to a seasonal energy efficiency ratio based methodology took half a decade and the other half before it will be implemented in full. The pace of regulatory change covering the use of very mildly flammable refrigerants is also a major barrier to their adoption. So let's get into this. So if you look at where energy is used in buildings, 16% of New Zealand's total electricity consumption is used in non-residential buildings, of which a third is used for lighting, a third is used for HVAC, and this has a value of around $1 billion a year. 7% of our national gas consumption at a value of $650 million a year is used in water heating and space heating within our buildings. Smaller buildings use the highly familiar split package air conditioners and heaters, whereas larger buildings tend to have much more centralized HVAC systems. Over the past 20 years, we've seen we've gone from a platform of water source air conditioners, and they have been replaced by VRF-based systems, which use, instead of using water as an energy carrier in buildings, we're directly using refrigerant as the energy carrier. And if you look at the amount of energy per square meter in commercial buildings, it's about 4 times that of residential buildings. So looking at the sort of key drivers to change, the first big one is the rating standards by which our products need to meet as part of their energy efficiency performance standards. So we moved from having sort of fixed test points which favour sort of fixed speed style units to a seasonal energy efficiency ratio methodology that very much drives us towards using variable capacity systems. The reality is that these units operate in part load the vast majority of the time, and this drives us towards using inverter-based systems with variable speed fans and variable speed pumps and variable positioning EV valves, and you get increased efficiency, but it comes at a significant increase in the technology. And it's also for smaller systems a H2 low ambient test point. And you can see that the rating, the star rating labels are changing from those on the right to those on the left, where there's more information about the zone efficiency in different zones that the products are rated for. And if you look at this sort of bin profile for New Zealand air zone, the traditional test points H1 and H2 are labelled, and you can see the number of hours that the systems are actually operating in a part load state, where it's much more mild, either in heating or cooling, than what the traditional rating points have been. And if you look at the effect on the efficiency of units in these part load conditions, the red and the blue graphs show how much the efficiency of these systems increase as the temperatures become more mild and as the inverters slow down, and you get very big effects of system efficiency with under part load conditions. The other big driver of the industry is the Kilgardy Amendment. It's the HFC phase down. This is where we need to start changing our refrigerants that we're using. And this is a part of a global platform that worked out that we can reduce by 2100, half a degree, which is huge, of global warming through phasing out these very powerful greenhouse gas refrigerants. New Zealand ratifies the Kilgardy Agreement in a few days' time, October the 3rd, and implementation is January the 1st. Now, we lose. If you look at how much refrigerant gets imported and where that refrigerant goes to into installed products and recovered products and that, there's 486 tons of this refrigerant lost to the air each year in New Zealand, which is the equivalent of 1.1 million tons of CO2 equivalent, which is the equivalent to 540,000 vehicles on our road in terms of emissions. Now, this is not just air conditioning, this is the entire refrigerant use, so it includes the refrigeration industry too, and the vehicle industry too. 1 kilogram of a R14A released into the air has the annual emissions of one vehicle. There's some pretty powerful greenhouse gas chemicals. So we've got to change, and one of the big problems we're changing is that when we move away from R14A that we use today, and we look at what the alternatives are, they're either far less dense, so we need to make much bigger units, or they're flammable, or they're explosive, or they're toxic. It's been quite a lot of difficulty for the industry to choose which one to adopt. Timzone has decided upon R32, and we're the first, we understand, global manufacturer of commercial air conditioning systems to use R32 and variable speed product. Most residential air conditioners are already converted, all the high walls that you will buy today are now R32. Our transition to commercial products is very much underway. It is very mildly flammable. There are charge restrictions and occupied spaces. It's more efficient. We use less of it. And what we've found is that we can achieve between a 75 to 80% reduction per kilowatt of cooling capacity in carbon and greenhouse gas emissions, and much better heating performance too. Most manufacturers of R32 are labelling it green. The truth is, this is a stepping stone. It's an interesting situation because we know when we have to phase out of R32 before we actually start using it, and around the mid-2020s, we will need to start using the next generation of refrigerants. It still is some moderate greenhouse gas chemical. One of the big changes for the industry is you just can't pump large volumes of this stuff around buildings in the way that we have been with our R14A systems, and we see water being increasingly used as as an energy carrier around buildings. So if you look at hydraulic style systems, which is where we're moving kind of back towards, the system on the top left is a 4-part very conventional chiller system. It's got a chilled heated water system. It's got a set of flow and return cold pipes, flow and return heated water pipes, a bunch of fan coils or valves controlling the flow through them, and the chilled water is made by large chillers, usually up in the roof, and there will be a gas boiler usually in the basement of the building. Other forms of hydronic systems are water source style systems, such as where you have a water loop that you reject or absorb the heat out of for heating and cooling, for cooling towers, and gas boilers, again, reconditioning that water loop. If you look now at where we can go with making changes to the products that we offer, if you look at energy efficient air conditioning first, the technology in these products is increasing a lot. So we've got variable speed, BLDC, ultra efficient plug fans and BLDC drivers and variable speed pumps and expansion valves and system controllers, and these are all the sorts of components that you'll be seeing in our next generation variable capacity air conditioning systems. One of the big areas where you can make a large impact on the cooling loads is to change lights, and we're finding that when sites are changing to LED lights, the reduction in heat load is putting much less load on the air conditioners. Another big area is to use whole of system controls. The better controlling these products makes a very big improvement in the efficiency of them. In terms of heating system, the focus has to be on the increased electrification of these systems. It's really, the transition is all about removing fossil fuel heating options from buildings or using them sparingly where they're needed to do peak or burst heating rather than the larger base load heating. And in order to do this, we need to start replacing, there's thousands of our New Zealand central boiler systems with big distribution networks of primary circuits, and off that primary circuit, you've got space heating and water heating, heat exchangers to secondary circuits. But the big differences you can make is to pull apart the centralized boiler loop and do distributed heat pump systems around the building, which are supplying the right amount of heat at the right temperature at the right location around the building. And what this allows you to do is to decouple your space heating, which only runs half the year, from your water heating, which is usually much lower loads. In terms of water loops, we need to start replacing reconditioning boilers and electric heater banks with heat pumps. We need to design heating systems to much lower supply water temperatures, so that heat pumps can be, so the temperatures are within the range of the heat pump systems. And we need to start using much more thermal storage using off-peak renewable electricity. The little graph on the bottom right shows the emission factor of different fuel types. You can see coal and gas relatively high, electricity, and then heat pumps and wood are much lower emission intensity systems. In terms of water heating, there's a range of options. that we can adopt is a large proportion of our national energy consumption. You've got electric, solar, and hot water heat pumps are the main options. We need to reduce the use of ring main systems and how we control them. Evacuate tubes for higher temperature applications, flat panels, solar for lower temperature, effectively better integration of different technologies for water heating. In terms of the future, we need to start reimagining how we provide HVAC services. The traditional 4-pipe chilled heated water system, you can make a very large change to the energy efficient, or improvement to the energy efficiency of these systems by just supplying the correct flow at the correct temperature, water directly to the zone that needs the heating or cooling, using 6-way valves and central manifolds of flow and return rather than piping heat and chilled water continuously around the entire building, using single core multi-row fan coils that can work within the temperature ranges of chillers and heat pumps, and starting to use 4-pipe with heat recovery chillers. Another option is another pathway forward is the integration of demand response systems. There was a consultation about this quite recently. This is this idea that air conditioners and heating systems contribute significantly to the peak demand on electricity networks, and that there's a responsibility on the supplier of these products to allow the network to manage their use or their demand when the loads on the networks become too high. And this has been done by a proposed standard, NZS 4755, which allows a network operator to send a demand response signal to appliances, and connected appliances then reduce in their power consumption. Over time, I see that this is really going to drive the better utilisation of network capacity and avoiding the inefficient over investment into the grid. And we need to create capacity within our electricity networks to better integrate renewable energy and to support the increased electrification of our transport sector. Another big area of change is, as I said, the R32 is a stepping stone to a zero GWP refrigerant era. There's other natural refrigerants of hydrocarbon, ammonia, CO2, and the synthetic HFOs. At this point in time, the regulatory environment doesn't support the mass use of many of these alternative refrigerant and the scale and classes of products that are used within the industry. But we see post mid-2020s, the regulatory environment will slowly catch up. CO2 is already very common in supermarket chiller systems, largely as a result of the very high rates of refrigerant losses historically from these systems. And then there's the integration of the solar PV with the HVAC sector. At the end, already we've got the ability for our inverter drivers driving our compressors to directly communicate with the PV inverters on grid-tied systems. And with cooling loads, the two are in phase. The sunnier it is, the hotter it is, the more energy there is available, and the greater demand there is on the aircon system. With heating systems, you need to have a thermal store. Concrete floors work very well for doing this. The next stage, I would like just to run through a few projects that demonstrate some of these principles in action. We've designed a range of heat pump water heaters and chillers, which have a key principle that for a given supply of water temperature, the cooler or the warmer and cooler mode, the return water temperature is, the more efficient the system is. And that key principle has been applied in a range of different products which are focused on different applications. And we tend to use, rather than directly controlling capacity, the inverter capacity by changing the inverter speed, we're doing it through variable flow systems. So the temperature of the return water and the volume of the return water is what's creating the signal for the compressor to either speed up or slow down. And it leads to highly simplified controls, which is proven very effective in application. And the whole drive towards this is to exploit the part load efficiency of available capacity systems. So we looked at a very typical KFC store that's got a hot water demand, a fresh air tempering demand, and we had a look at what we could do to make this type of system more efficient. And we came up with a single pass water heater that's working on a thermally zoned tank. This class of water heater takes cold water from the bottom of the tank and heats it in a single step and layers this 62-degree water at the top of the tank. And then that 62-degree water enters into a small tank on top of the main tank, which is heated electrically between 65 and 68 degrees C to meet the kitchen health, safety, temperature of 65-degree water at the tap. And we've used the spare capacity of the heat pump to supply the energy required for a fresh air temperature coil, and this is controlled using a variable speed pump. This is what it looks like in practice. This approach has effectively halved the size of the heat pump that we otherwise would have needed to meet both the loads required. We had a monitoring system installed. We created a live animation for the customer to look at. You can see it's taking the 10-degree outdoor air and it's heating it to 18 degrees within this system. And then we get really, really detailed data coming back off this system. You can see the kitchen hot water operating within a very small band. And you can see how well thermally stratified this tank is by how much the temperature within the tank changes, which is the sharpness of these troughs as this thermal stratification boundary layer moves up and down past sensors. And the stores use around 2,200 litres of hot water a day. We achieved a COP, a season COP of 3.4, which correlated to a reduction of 68% reduced in electricity consumption. If you look at the system, had it provided the same heat purely electrically versus using the heat pump, we've reduced the proportion of the total electricity usage in the store from 23 down to 8%. And this has got the equivalent energy savings of 23 electric vehicles traveling 50 k's per day every day of the year. Another project was to take a central boiler system and do a distributed heat pump system. So the two large heat pumps here are twin stage each inverter systems doing with the space heating, the radio networks within the building, and the other boxes are doing the potable hot water. So separating those two loads. And we've done this on 3 hospitals, so Barve Islands, Dargaville and Kaitaia, and the energy savings from doing this, 282,000 litres of diesel, 794 tonnes of CO2 each year, and a lot on maintenance and energy costs also. Another project in Sydney was to take a supermarket that had a 120 kilowatt electric heater bank and replace that with a heat pump water heater. It's a very simple system. The heat pumps is controlled into a supply air temperature, and that still saved 243,000 kilowatt hours a year in energy saving as a result of doing this. Our final project was a YHA backpackers Mount Cook, worked for the company Sunshine Solar in Christchurch, and they've taken out a gas-based heating system and have done solar PV, hot water heat pump, solar thermal integrated system. This is the first example that we know of where a single pass solar thermal system has been meshed with a single pass hot water heat pump, and so that neither technology competes with the other. They're highly synergistic, and this project here has no gas supplementary heating. It heats an 80-bed hostel all year round, using only solar thermal and hot water heat pump. So to conclude, these types of projects have driven much of the technology development at Tempzone over the past few years. This work has been supported by the use of the Splash IoT platform and has allowed us to take much greater risks in new product development as we look at how technology can drive towards greater efficiencies and reduce emissions from our built environment as we develop a next generation of products. I don't claim to have all the answers, and there's very much work left to do. I do, however, welcome your questions. Thank you for listening, and thank you to the New Zealand Green Building Council team for their work in developing a more sustainable environment for all of us.
Thanks, Adrian. That was really interesting. Thanks for sharing all of that information with us. I'm sure we will have a few questions. So if you can get your questions through to us now, just enter them in the little box and we'll have a bit of time. So we've got our first question. Adrian, your data, i.e. comparison to cars, is frightening. Thank you for the eye-opener. As an architect, when I request the specification of a system, what design standard and or guidance document should I be asking my HVAC designer to comply with? Is there one? Obviously, the New Zealand minimum standard does not address a low carbon future.
The short answer is no, there's not really one. We're doing a lot of work in trying to create application manuals for new products. This really is an area where there's so much work that needs to go into transforming a service-focused industry into a much more renewable energy efficient focused industry.
So the next question is, please provide a link to download the slides. You okay with us providing that?
We can certainly do that, yes.
So we'll send that out in the follow-up email that we'll send to you later, hopefully today. So we'll go on to the next slide, but if you do have any questions, we still have a few minutes left, so you can still send those through. If you haven't seen already, we launched our zero carbon roadmap for Aotearoa's buildings, so make sure you have a read of that. It's at nzgbc.org.nz/zero carbon/roadmap. And it's also World Green Building Week this week. Here in New Zealand, we have upcoming events in Auckland, Hamilton, Wellington and Christchurch, from panel discussions, further webinars, workshops, film screenings and a nationwide photography competition. There's definitely an event for everyone. All the information can be found on our website. Go to nzgbc.org.nz and find upcoming events. So we have another question that's come through. Are heated or, I think that's called, are heated or cooled floors embedded in cement a viable CO2 reduction solution in your view?
So heated floors is a really interesting one. So it certainly provides really great thermal comfort. I think this idea that you can do highly zoned heated floors or is going down the wrong track. I think heated floors providing a warm, dry, healthy environment is highly desirable as a background, so base load heating. To sit on your phone and directly control the temperature of each zone of your floor this way, I'm far more skeptical about. In commercial applications, this idea of pre-cooling beams using nighttime running units at nighttime is a very attractive pathway forward. The energy efficiency of producing a cooling effect at nighttime is very much higher than during the daytime. So I think having energy storage within buildings is a really good idea. It's very much a viable pathway forward.
Great, so it looks like that's it for questions at the moment. If you do have any more questions, you can send them through. Oh, there's another one come through. What are the classic installation problems seen on site by installers of HVAC systems that cause energy loss in HVAC systems? What should we watch for?
I think one of the really big ones is ventilation. You know, we have so many systems which are where the ventilation load is sized for the maximum occupancy possible for that space, but the number of people actually in a space at any given period of time is usually far smaller. And the simple use of CO2 sensors and variable ventilation loads makes a huge difference in the operational energy consumption of buildings. I think too, under or oversizing things, trying to save money on having ductwork and high static fans in that is missing the point somewhat. You need to very much be looking at the long-term operational cost of these systems.
All right, that's all the time we have. If you do have anything else that you're dying to ask, then send those through to education. Our education team will help direct them in the right place. So as always, we value your feedback and want to make our webinars as appropriate as possible. So please spare a few minutes to fill out the feedback at the end. Let us know how to make them even better. Thank you and enjoy your World Green Building Week. Thank you, Adrian.
Thank you.